Hi, I'm James Harper. In this video, we're going to talk about the basics of hemostasis. The learning objectives for the video are to describe the basic clotting system, the role of vitamin K and calcium, and the role of coagulation complexes in the clotting system. The function of a clot is to fill the breach in a blood vessel and to help stabilize the fractured vessel while it can heal. Clots form in the context of a vessel that has flowing blood, shown here with the arrow, is surrounded by tissue, and it's surrounded by endothelium, which is by design largely anticoagulated. The clot is formed with a shear effect, and the downstream side is washed away, much like a sandbar in the river where the water flowing over it washes the downstream side away. The clot has fibrin strands which project out from the broken vessel into the surrounding tissue. These function to stabilize the clot and to act as ladders for neutrophil in-migration into the wound area to facilitate wound healing. You'll note though that the clot stops, and this is because of the effect of endothelial expressed thrombomodulin, which is involved in the process of converting thrombin washed downstream from the clot to activate protein C, which is a potent anticoagulant enzyme. The effect of activating protein C here focuses the clot, much like a lens. The coagulation pathway, in terms of enzymes, is a complicated one. The combination of tissue factor and activated factor 7, this little a at the end, activate factor 9 and also activate factor 10, creating factor 10A. Factor 10A activates thrombin, or from prothrombin. Thrombin activates fibrin from fibrinogen, and then fibrin strands are stabilized and cross-linked by a factor called factor 13. This process is amplified by the blue loop, and thrombin activates factor 11, which activates more 9, and the combination of 8 and 9 activate more 10, and then 5 is activated as well, and the combination of 5 and 10 activate even more thrombin, which results in more fibrin and a burst of activity of both thrombin and fibrin. The coagulation pathway can be thought of like a radio. The tissue factor is expressed from the broken blood vessel and picked up by the 7. That's the signal. Now, this process here goes on without the amplifying loop, but does so at a very slow rate, and the clot that's formed is weak. This amplifying loop, manifested here by the stereo amplifier picture, this amplifying loop amplifies the clotting process thousands and thousands of times, thus resulting in a large burst of this activity, which creates a large amount of fibrin, and a strong cross-linked stabilized clot can be formed. Thrombin is normally an enzyme which is not active, and it arises in a burst. The burst then parallels the amount of fibrin laid down. It's important that thrombin burst be considered because thrombin activation and the anti-clotting protein called plasmin is also activated at roughly the same point. Given thrombin activation, more fibrin can be laid down rapidly and can inhibit the effect of plasmin. And here we see a normal thrombin burst. And here we see a weak expression of thrombin in a child with hemophilia, where whom the amplification loop we talked about doesn't work. The clotting system exists in intimate connection with membranes. The endothelial cells and platelets are deeply connected and deeply important in the clotting system. Tissue factor and 7A, again, the antenna receiving the signal of the fracture, activates some 10A in the presence of expressed activated factor 5A, activates thrombin. Now, thrombin is important for a couple of reasons. One, it is less dependent on membrane than factor 10A. And two, it's essentially the Swiss Army knife of the clotting system. It activates factor 5. It can activate platelets. We've already talked about how it can affect fibrin production. And it activates one of its amplifying enzymes in pulling off factor 8A from the complex of factor 8 and von Willebrand factor. So if you think about it, this enzyme can actually induce its own creation. If in terms of once it's turned on, it can turn itself on more because it can turn on the amplification loop via more factor 8 and more factor 5. Factor 9, along with factor 8A, factor 9A and factor 8A, can activate factor 10A, and this in the combination with 5A activates thrombin. This complex, 9 and 8, are called tenase. 10 and 5 are called prothrombinase. 2 is called prothrombin, and 2A is called thrombin. Membrane involvement is, as you said, very important. The vitamin K dependent factors, all made in the liver and undergo post-translational carboxylation in a vitamin K dependent process. These are referred to commonly as the vitamin K dependent clotting factors for that reason. People who don't have vitamin K still make the protein. They just don't make good protein that works. People with vitamin K dependent clotting factor deficiencies have slower clotting time and bleed more. And we'll talk more about those issues in later videos. Vitamin K dependent clotting factors attach to the membrane using phosphatidylserine moieties largely, and are bound to the membrane, at least in part, by calcium ion bridges. Factor 8 is not phosphatidylserine dependent, and this allows that tenase complex to be much more effective than factor 9 by itself. And one can think about this if you held your hand out and you brought your fingers up like you were trying to grab a baseball or an orange. And you imagine that each one of your fingertips was a phosphatidylserine, and all the space between your fingertips was something else. If factor 9 was hanging on your thumb, and a factor 10 was hanging on your index finger, in order to make that connection and activate the factor 10 would be to have the factor 9 be close enough to the 10 to work. Okay. Now imagine you had a ball instead of the empty space, and that ball could hold 9 and 10. Then you would have all the fingertips open to receive the 10As you made, and the 9 could sit in that little comfy ball and just pump out 10As for a long time, right? And that's basically the clotting complex called tenase. Okay. So we've talked about 10-ACE, and prothrombinase is basically the combination of activated 10A and activated 5A on the surface of a membrane involved in a clot, per platelets or endothelium, largely. Um, and this allows rapid conversion of prothrombin. Protein C-ACE is the clotting enzyme complex downstream from a clot. This is what focuses the clot and allows our first clot to not be our last clot. Protein C-ACE is a combination of endothelial protein C receptor, or EPCR, and thrombin, which is activated factor 2, and a protein called thrombomodulin. This causes thrombin to convert from a fibrin activator to a protein C activator. And when a large amount of thrombin can be converted like this, a large amount of protein C is made, and then at least locally has the effect of inhibiting the clotting system in that area. And again, we'll talk more about protein C in later videos. So let's talk about the basic clotting studies. You've probably ordered these in your preclinical training. Prothrombin time, or the PT, the partial thromboplastin time, or the PTT, the thrombin time, and the euglobulin clot lysis time. The prothrombin time is called the poor man's liver function test. And the reason it's called that is 7A. 7A has a very short half-life. In children, 2 to 2.5 hours. In adults, more like 4 hours. But again, compared to all these other clotting factors, this is very short. And this thus gives you a sense of how the liver is working, hour to hour, because a certain fraction of the factor 7 made is activated in circulation. And so basically the antenna is always open for a signal from the tissue factor. Absent that clotting factor, the initiation steps, which are what measured in the prothrombin time, become slower. The partial thromboplastin time measures the amplifying process. The classical reasons for partial thromboplastin time problems are deficiencies of factor 8 or factor 9. Factor 11 deficiency can also cause it, but typically these enzymes produce a prolonged partial thromboplastin time. The thrombin time is a test where activated thrombin is used to measure or to convert fibrin from fibrinogen in the patient plasma sample, and the time it takes to do that is measured in seconds. This looks for anomalies of fibrinogen or fibrin, as well as potentially anomalies of thrombin, although that can be found other ways. The euglobulin clot lysis time measures the effect of factor 13. While factor 13, like all the clotting enzymes, can be measured directly, it's costly, and this test is more a physiologic test, which can be used as an effective screen clinically. And then if this test is abnormal, the enzyme can be measured, thus saving your patients some money. Okay, so the PT and the PTT, these are things which you will order frequently in your patients, and they're basically 3 outcomes, aside from normal. The PT can be prolonged and the PTT can be normal. The PT can be normal and the PTT can be long, or they can both be long. Where is the anomaly? In the case of the PT being prolonged and the PTT being normal, you know it's factor 7, deficiency primarily, because if it was factor 10 deficiency or factor 5 deficiency, this would be abnormal as well, right? PT normal, PTT prolonged, again, that's the amplifying circuit. That's factor 9 or factor 8 or factor 11. Why not 10? Same problem. 10 was going to cause your PT to be abnormal, right? Okay, so if they're both abnormal, the first thing to think about is multiple deficiencies. Liver failure doesn't just cause a deficiency of one thing, it causes a deficiency of all things that are made in the liver. Now, it's true that factor 7 is made quicker because it has a shorter half-life. And so factor 7 deficiency can be the first shot across the bow of a liver that's giving up the ghost. But by the time most people get to the doctor, the clotting factors made by the liver are wildly abnormal, and thus the typical problem will be prolongation of both clotting factors, both clotting tests. So when this is abnormal, factor 7 deficiency of some kind. When this is abnormal, amplifying circuit, factor 8 or factor 9 typically. When both of them are abnormal, final common pathway, and multiple factor deficiencies. Okay, so we're going to do some review questions. Now, during these questions, if you have to think a bit, pause your YouTube player and then push play after you've selected your answer. Question 1. A child had a liver and small bowel transplant. Because of this, he has a large piece of his duodenum removed and is chronically vitamin K deficient, because vitamin K is absorbed in that part of the stomach and intestine. How will this affect his ability to clot blood? A. There will be a decreased amount of clotting factor protein produced in the liver. B. The clotting factors will attach to the membrane by binding calcium through other means. C. Non-vitamin K dependent factors will increase their reaction speed to make up for the loss. And D. The activity of the activated vitamin K enzymes will be markedly reduced. And the answer? D. Vitamin K deficiency is rarely total. And so while there will be a prolonged clotting abnormality, it will not necessarily completely wipe out the clotting system, although certainly there are people with vitamin K deficiency of such severity that their clotting system is completely deranged. Okay, next question. The role of the coagulation complexes in the cascade is to A. Improve the efficiency of the actual catalytic enzyme. B. Form new catalytic enzyme from the parts of parent enzymes. C. Bypass the need for calcium in the clotting system. Or D. Cover more of the membrane with enzymes. And the answer is A. To improve the efficiency of the actual catalytic enzyme. And an example of this is the factor 8 functions a lot like a Tinder bundle on one of those survival shows, where the guy cups his little coal in the tinder bundle and then blows on it to try to make the tinder bundle light on fire. And the factor 8 is sort of like that. It's that ball in the middle of your fingers that allows more factor 9s to activate factor 10s and have a place for the factor 10s to bind to the membrane and turn on. Question 3. Billy has classical hemophilia, which is factor 8 deficiency. He is studying for his disease in his school. He asks you, when he sees you, how his disease makes him bleed more than other kids. So of the following, the amplifying effect of the extrinsic pathway is lost. B, factor 9 can activate factor 10 without it. C, factor VIII is necessary to make the vitamin K dependent clotting factors. And D, 10A doesn't bind to phosphatidylserine without factor VIII. And the answer is A, amplifying effect of the extrinsic pathway is lost. Absent the non-dependent binding of factor VIII, factor IX's catalytic activity is thousands of times slower. Again, if you think about your hand held like you were holding an orange in your hand, the phosphatidylserine sitting on your thumb has to bind to the inactive 10 on your index finger and then leave it float over to one of the other fingers. And how likely do you think that's going to be? Especially if the factor 10A isn't on your index finger, but rather on your ring finger, farther and farther away. And so the enzyme activity of factor IX is radically improved just by proximity to the factor 10 and binding sites for the factor 10A. Okay, this is the end of this video. Go ahead and click out of your YouTube browser, and then you'll be taken back to the rest of the Prezi videos. If you have any questions about this, email me at jlharper@unmc.edu.